Okay, so in yesterday's class, we were delving into negative feedback loops in a more formal fashion. And where we stopped, this is where we were. So this is the classic topology all of you are familiar with. The one we are more interested in this course is the following. And we drew some analogies between the circuit on the right and the circuit on the left. And the critical difference that we saw was that in the circuit on the left, each of these blocks, that is G and H, seem to be behaving like the other one was not existent. That is, regardless of whether H is connected to the G or not, the gain between the input and the output of the forward path remains G. But on the right-hand side circuit, that's not the case, because whenever you make something with whenever you connect two electrical networks together, you'll have to be aware whether the one that you are connecting is loading the previous network. In this case, obviously it does. Now, if you have to ensure that whatever this contraption that you are planning to load should not be loading it such that the open loop transfer function of the amplifier, the transfer function of the amplifier, or the gain of the amplifier in this case, doesn't get affected. Okay, so that we can do by just ensuring that this total resistance, that is KR, should be much greater than RD. If that is the case, then it will not load the amplifier either in the quiescent state or even in the incremental state sufficiently. So that can be solved. So now, before going into solving this, going forward with this, let me quickly point to some of the very interesting features of negative feedback loops, which I'm sure you are aware of from 250, but for the sake of continuity, let's delve into it for some time. So let's say that I inject the current, a small signal current, let's say delta I. Okay. And let's assume that the loop is not there at the moment. Let's assume the loop is not there. That is, this is broken. This is all you have. Okay. And assume the amplifier is biased, and also biasing is not an issue. So if you push in the delta I current and neglect channel length modulation for the transistor, what do you think V0 will be? Delta I into KR parallel RD incrementally, right? They come in parallel. So delta I into KR parallel RD. Fine, simple enough. Now let's assume we have connected this. And if you assume that this loop gain is very high and GM is very high, like GM tends to infinity, let's say, for the purpose of this analysis. So what do you think? What is your intuition telling you? What will delta I be? So will it be delta I times RD parallel KR, or it will be different? It will be same or different? That much should be pretty straightforward, right? Will it be same as when the loop was connected and now, or will it be any different? Is the question clear? Am I audible? Okay. So what is the question? Pardon? Yeah. So in the when the loop was not there, it was pretty straightforward. The delta I was going into a parallel combination of RD parallel KR. So the output voltage would have been delta I times RD parallel KR. But now when I have closed the loop, now will it be different from that case or will it be the same? It will be the same. Okay. So what's the, I mean, why do you think it will be the same? Okay, so there will be no current through the transistor. Okay, so why do you think there will be no current through the transistor? Okay, fine. So from the device perspective, he is saying this is an oxide, so no current should, I mean, flow through the transistor. But when I say current flowing through the transistor, I don't mean current flowing into the gate, right? I mean current flowing between the drain and the source. Pardon? Yes. Okay, so don't do GM 10 into infinity now. Let's assume that GM is a finite value, right? GM is a finite value. So will there be any current flowing through the transistor? Yes. Okay. So now, okay, so let me simplify stuff. So let's say VI is not there. VI is grounded. Okay. So now do you think VG is 0, the gate of the transistor? So we have this thing, right? So in the absence of feedback, there was no connection between output and input. Now, when I've connected the loop, there is a connection. So gate will not be 0 or floating or anything. There is a connection between input and output. Rather, in this case, from output to input. So if you excite something at the output, its effect will come to the input. Okay. So now, in this case, how do I? So now let's assume that this happens. Let's do the qualitative effect first, then we'll do the quantitative effect. So now let's assume GM tends to infinity. Okay. And if I push in delta I, wherever I have, so this voltage will tend to increase, which means this voltage will tend to increase, which means this voltage will tend to increase. So the gate of the transistor will tend to increase. Now, if the gate of the transistor tends to increase, what will happen? This transistor will get activated and it will sink in the current. And if you have GM to be infinity, right? Or in this case, yeah, so let's assume GM is extremely strong, then all of delta I will flow into the GM and nothing will flow into RD parallel KR. Right? So what will be V0 then? V0 will be 0. So if GM tends to infinity, which means GM is infinitely strong, right? So this excitation that would have happened here would have flown through here and it would have excited the GM. Moment it excites the GM, it sinks in the current. And since it is infinitely strong, it will be able to sink in entire delta I. I mean, this one, whatever I have applied. So this is an external injection that I have given. No. So this delta I is not transistor current. This delta I is some external current. I am perturbing the loops separately. This is a separate current source. The question is, if it's a negative feedback and I perturb the output of the negative feedback with something, will it affect the loop? Will it affect the output? Right? So this analysis seems to tell us that it will not. Right? Because if delta I, if I push in, if V0 tends to increase, the gate of the GM will tend to increase and it will pull in the entire delta I. right? Whether entire delta I or some fraction of delta is a matter of analysis, right? We'll get there. We'll get there, right? So at least this much should be acceptable, that if some fraction of delta I will go into get into the GM, and not as much will flow into the parallel combination of RD parallel AR, which means the voltage will not at the output will not jump as much, right? So now let's see what happens if GM is very large, if GM tends to infinity. Okay. Or in this case, let's assume that GMR or the loop gain is infinity. So if the loop gain is infinity, what do you think will happen? Okay, so forget about this delta, I think, right now, right? So if loop gain is infinity, what do you think? And you have VI here. What do you think will be this voltage? Input of the amplifier. Let's say delta is not there. So note that if I have to draw the analogy between these two circuits, this is the feedback voltage, right? This voltage is VI minus VF. And G is an amplifier having, let's say, infinite gain. Okay. So this becomes AV times VI times VF. So this is equal to V naught. What I'm asking is AV equal to infinity? What will this voltage, error voltage, VEB? It will be 0, right? That's what we did. We saw that, I mean, the solution to this equation under the condition that AV tends to infinity is VI is equal to VF, right? So V will be 0. Now go to the circuit on the right. What am I saying? I'm saying the gain of the amplifier is infinity by setting GM to be infinity. So what do you think this voltage will be now? It will be 0. It will not get excited. And does it depend on whether I have applied an input or not, or I have applied an input anywhere? It doesn't, right? So this still remains the same. This is VF fed back. This is also VF. So the gain times VF, right, is supposed to be some finite value. And if the gain is infinity, VF has to be 0, right? So in other words, the other intuitive way of thinking about it is, if you agree with the fact that in the presence of a finite GM, some fraction of delta I will flow into the GM and lesser proportion of it will go into the resistances. Okay. So now what happens if I increase the GM? Will that fraction that goes into the GM increase or decrease? It will increase. And if I keep on increasing it to infinity, the fraction that will go into the GM will be almost 100%, which means nothing will go into the resistors, which means output will not get excited anymore. Okay, so this is an extremely important property of our negative feedback loop, that if you excite the output of a negative feedback loop with any disturbance, assuming the loop is biased properly, designed properly, you'll not be able to move the output. This is a good property because it rejects any disturbances when you are probing, when you are trying to disturb the output of the negative feedback loop by any means. Okay, so this is basically noise resistant, interference resistance, or whatever bad things you can think of is resistant to that, as long as you are trying to influence the output by probing it at by inserting any disturbance at the output node. Yes. GM is large. If GM is large, majority of it will flow through the GM. Right? So that's what I mean. You can, the analogy between these two blocks are, if you apply an input here, or let's say a disturbance delta V here, and go around the loop and find out what V0 will be. Right? So the only thing sacrosanct about the loop is the fact that this is a virtual ground node. And this the amplifier is amplifying the error. So in circuit parlance, this is often called an error amplifier, right? So input of the error amplifier goes to 0 if the amplifier gain is close to infinity, right? If the amplifier gain tends to increase, the input of the amplifier will tend to decrease. Okay, and that is the only fixed property of a negative feedback loop. So you can analyze how the loop works by simply figuring out what is the input of the error amplifier, and you set the input of the error amplifier to 0, and then go about analyzing the loop. Okay, you cannot analyze the negative feedback loop in a forward direction, because what is happening is in the forward, as you can see, if I try to analyze the loop in the forward direction, then the problem that you will face is, this is like dog catching its tail, right? The output gets excited, the feedback function comes back, and it excites the input again, and it keeps on going round and round. And since so taking this example that we have been doing right now, if you had to analyze this in the forward direction, you probably would have needed the exact gain of the amplifier, right? But the negative feedback loop is constructed with the assumption that the exact gain of the amplifier is not relevant, as long as it is large enough. The only thing that is relevant is what is the feedback factor. If the negative feedback loop works properly, the feedback factor is what that sets your output, right? So now the feedback factor sets the output differently if the input is applied at different locations. If the input is applied here, your output will be 1 over h. But if the input is applied here, it will be different, right? But nevertheless, the output will be set by whatever is connected in the feedback part, not in the forward path, because the forward path is supposed to give you, the only job of the forward path is to amplify the error, and it has to be large beyond certain pitch. Okay. Okay, so this is critical. So now, yes. Summer, yeah. Correct. So as long, again, yeah. So the other way of saying the same thing is, whatever happens to the universe, it doesn't matter if the gain of the negative feedback loop is infinite, this voltage will not move, right? So everything else might change, that will not move. Then if you know something is constant, you can go around the loop and figure out how it gets affected, how the loop gets affected, provided gain is infinity. Now, obviously, gain will never be infinity, right? It will be large enough, so which means there will be some error. Okay, so let's go back to the classic model. So now my V naught over Vi is G by 1 plus GH. This many times we like to express in this format, 1 by H. Yes? Question? Okay. In this format. The reason we like to express in this format is because GH is loop gain, right? So this is 1 over H, L by 1 plus L. Now this 1 over H is the desired output when L tends to infinity, right? This is what we started off with. This is what we targeted. So V naught by Vi when L tends to infinity is 1 over H. This is what we targeted. Now, if L is not infinity, there is an error. And how much is that error? Error is 1 over H, 1 minus And in terms of percentage, and if L is really large, right, that's what typically a well-designed loop is. It is 1 over H. Sorry, error percentage is. This is the error. If I do error percentage as in, you have to divide by what is the expected thing, right? So expected is 1 by H. I'm dividing it by that, and this approximately becomes. This is the absolute error. Becomes 1 by L times 100. So the error in a negative feedback loop is inversely proportional to the loop gain, and that should make sense, because if loop gain is infinity, right, the error should go to 0, right? So we designed a negative feedback loop assuming we have an infinitely strength amplifier. If you have an infinitely strength, if you have an amplifier with infinite strength, then the error will go to 0. Which means that this should not be of any surprise. So this is an important outcome, important analysis for negative feedback loops, because if you are in charge of designing the loop, right, and I tell you that I am looking for a 1% error, right? I'm looking for a 1% error at the output from a desired maximum output that maximum error that you can have is 1%, right? So the first thing that you have to figure out is what does that translate to L, right? What does it mean with respect to L? Then you know that if I am asking for 1% error, means L is how much? L is 100, right? So you have to design your loop gain for 100, and loop gain is in your control, right? Part of the loop gain is the amplifier, which means the gain of the amplifiers needs to be at least 100, right? Obviously, you will not be making an amplifier of gain exactly 100. You have to keep some margin, and maybe you make 200 or 300 or something, or 150, depending upon what is the variation of ambient conditions that the amplifier can tolerate. But you have to ensure that across all variations of ambient conditions, the loop gain has to be 100. Okay, then you can always ensure that the error is less than 1%. Now, if for another application, if you require error less than 0.1%, you have to find out the loop gain and figure out the gain, and you have to design your amplifier for gain equal to 1000, right? So that's how your top level specifications with error will relate to the loop gain. This is important again because when you are designing something for a customer or for any product, your end user is not particularly concerned how you have made the circuit. The end user is only concerned about what is the input to output relation. And if I tell you that I want an amplifier with a gain of 2, which is accurate within 0.1%, which means that you readily know that the feedback factor has to be 1 by 2, right? It has to be a voltage divider of 1 by 2. And you also know that if the guy has said that 0.1% is the error, I know the loop gain has to be 1000, which means the gain of the amplifier times the feedback factor has to be 1000, which means gain of the amplifier has to be 2000. So you go back and design the amplifier based on that. Okay, so that's why this steady state error, this is we call it steady state error because you see that there is no capacitance, no settling involved. So this is what will happen at when the dust settles which means that at equal to infinity. But the steady state error, or this error relative error, is a very important factor for designing a negative feedback loop. Yes. Okay, so if L is 1000, so you'll have to. So let's say I tell you that expected gain is 2, right? So it means GH is, which means H is 2. H is 1 by 2, right? So this is when I say expected, which means this, right? Which means H is 1 by 2. And if I tell you L is 1000, H is 1 by 2, which means the gain of the amplifier has to be 2000, right? You had a question. Okay, fine. So we demonstrated this stuff with so now question comes down to, if GM is finite, GM is not infinite, how will you go about figuring out how much change in delta V you will have? how much change in V naught you will have. You have to find if GM is finite and all the R's are finite, the gain will be finite. So you figure out what will be the steady state error, right? So in case of infinite loop gain, your V naught will be 0. But in case of finite loop gain, you will have some V naught, and that you can figure out by basically going around the loop and doing the math. So now tell me what will happen if I sketch the circuit again. Let's say I plan to inject an error here. So I plan to inject delta V here. Again, I'm not looking for an exact solution. Can you tell me whether this delta V that I have applied at this node will affect the output or not affect the output? Yes. The error percentage? Where? Yeah, so error percentage is relative to the expected value, right? So it's divided by this. That's why percentage, right? The top one is absolute error. Here it should affect, right? So applying delta V in the feedback path is equivalent to saying that I'm applying this delta V here also, right? So basically, if you go around the loop, I mean, you don't have to even apply that. You can just simply do the analysis. If this is delta V, this is supposed to be 0, right? If the loop works, that is the only thing that is holy. If this is 0, which means this is 0, which means this has to be what? This has to be? No, right? This has to be minus delta V. If this is minus delta V, this is R, this is K minus 1 R. What will V not be? Huh? No, right? If this is delta V, this current is minus delta V by R. It will be minus K times delta V. Why ID is 0? It's connected, right? It's connected to feedback, right? So if GM is infinitely large, you don't need any excursion here in order to feed in the current, right? Infinitesimally small excursion at the gate can pull in current. VGS is okay. If you are infinite gain, VGS is actually equal to 0, but it's tending to 0. Okay, so it's like you have done op-amps, ideal op-amps in negative feedback, right? What do you do with the virtual ground node? While analyzing, you set it to 0, and then you go around solving the loop, right? Yes. Okay, let's see. So if this is minus delta V, this current will be delta V by R, right? So same is this current, this is delta V by R. So V naught is minus delta V minus delta V by R is K minus 1 R, right? So this voltage and the extra drop, right? Yes. Infinite loop gain. Yes. Okay. So can VG be delta V if the loop gain is infinity? I didn't understand. VGS should be 0, but ground is, I have this is grounded, right? It's a hard ground that is not moving. Then why not we are taking delta V there? Okay, so then if I take the delta V there, you are saying this becomes delta V. Then ground. This is this is not a contradiction. If that is delta V, then this is looking for an infinite current. Right? So you are trying to pull in infinite current. Since you are trying to pull in infinite current, which means this voltage will drop. Right? So eventually the loop will settle somewhere where the input-output relation matches. And that matches only when this becomes 0. Okay. No, delta V value will not be 0. This gate voltage will go to 0. Gate voltage will be 0, and the effect of delta V will appear at BF. This will become minus delta V. Even though we are applying so it is because we are applying delta V here, the BF, this node will become minus delta V. Not even though, it's because. If I have a time, I have not shown the time dynamics till now because we haven't put any capacitor in place. But it will take some time. In the presence of capacitances, it will charge with the exponential and all those things, but eventually it will become. It will not become instantaneously, but in this network, in this circuit, it will become instantaneously because I have not shown any, we have not taken any capacitance into account. It seems like everything is instantaneous. Like we are applying delta V, so how come we have directly considered this minus? I'll come back to you. There was a question. Yes. No, it's not an impulse. You can assume this to be this. Yeah, it's a battery. You can assume it to be battery, but it's a delta V which is a step input, right? Okay, so his question is, can we go around the loop? Let's go around the loop. So in the loop, what is not going to change? You have to figure out something that's not going to change. In steady state, what's not going to change? Something is constant in a negative feedback loop. What is that? Input of the error amplifier. Right? Input of the error amplifier goes to 0, which means the VGS goes to 0. S is 0, VGS goes to 0, which means G has to be 0. Right? So this has to be 0. This is 0. So this is a summer, and the signal flow direction is this way, right? So if the input is delta V, output is 0. So, there are two inputs. One input is delta V, the output is 0. So the other input has to be minus delta V, right? Right. Right. Okay, fine. So this is sometimes when you are seeing it for the first time, it's slightly difficult to wrap your head around it. But so the way I would like to think about it is that instead of you can do this analysis two ways. One is you figured out, you assume that it's an ideal negative feedback loop. You set the error voltage to 0 and do the analysis. And if you are trying to figure out exactly what is happening in terms of dynamics, then you don't set the error voltage to be infinity. You set it, you don't set the error voltage to be 0, or you don't assume the loop gain to be infinity. You do this intuitive analysis that what happens if input is not 0, if this is not 0. If this is not 0, then and if the gain is very high, then you go around the loop and see whether the loop is tending to pull the gain, pull that error to 0. Right? You start off by assuming the error voltage is not 0. Then you go around the loop and see that whether the loop action is trying to force the error in the other direction. Right? Once you are going around the loop and trying to figure that out, as long as the gain is much, much higher than 1, then you know the loop is strong enough to pull it closer and closer to 0. Right? So that's how you can figure out intuitively whether this is working or not. Okay. Fair enough? Okay, fine. So now we'll have to move, and the only thing that remains in this network is what is the summer, right? When you are designing a circuit, nobody is giving you this box, nice box, which does this summation or difference, you have to make that also. So now let's okay. So for the time being, assume that the actual input is grounded, because we are analyzing the loop. The exact input is not relevant. So what I am trying to motivate here is that how do we get this right? How do we design that? Now, what is the purpose of this summer? In the small signal sense, what is it doing? It is taking the difference between these two voltages, right? It is if let's say this is V1 and this is VF. It is taking the difference between VF and V1 and feeding it to my common source amplifier. And the error current that I am getting is GM times VF minus V1. Okay, so this is simple enough. This is the error current that I am getting. But note that this current, if I look at a transistor in isolation, and I say that the current through the transistor, incremental current through the transistor is GM times VF minus V1, right? Given that you don't know anything else, what would you conclude? Let's say you don't know about negative feedback loop and anything, and I tell you have a transistor which is biased in saturation. Its current through it, incremental current through it, is GM times VF minus V1. Pardon? Yeah, so you would assume that V1 is the source voltage and VF is the gate voltage, right? Your transistor action itself does a difference. Does a difference amplification. Okay. So I don't need this summer, right? I may as well say that I'll get rid of this summer and connect this VF directly to the source. Right? That can be done. But how do I bias then? Looks like the source is hard grounded, which means I cannot hard ground the source. It should be incrementally grounded, but it should not be hard grounded. So given that you know all different types of biasing schemes, what is the simplest scheme that you can think of? Okay, so let me break the problem down. So this source cannot be hard grounded, but I want this VF to be connected to the source, which means I have to make a provision in order to ensure that the source is not hard grounded. So what can I do? But you have to bias first, right? Yeah, so, correct. VF should be connected to the gate, so I'll have to make that arrangement also. I have to do that flipping later on. So we'll do the flipping later on. Okay. But let's assume that you have to connect. Then what would you do? Yeah, his point is correct. His point is VF should be connected to the gate, not the source, which is correct. So we'll do that flipping later on. I'm trying to motivate. If you have to connect this to the source, what will you do? One problem at a time. I don't want the source to be hard grounded, but I still want this stuff to be acting like a good difference maker. So first thing, if I don't want the source to be grounded, I still want the transistor to be biased in saturation. What can I do? You have current sources and all. So the question is, let's say I have a transistor and I know that I have some voltage VF. Forget about VF. Let me call this V2. Let me call this V1. Okay. I want this V2 to appear at the source, or some fraction of V2 to appear at the source. Okay. So this source was initially grounded. So there is no way I can apply V2 to source if source is fully hard grounded. So which means I have to remove this ground and connect something there so that its transistor is biased still, right? If I simply connect V2 to that source, it doesn't look like, we don't know exactly whether the transistor will be biased properly or not. So how do I first set the bias of the transistor? Yeah, we can do, we can simply stick in a current source here, right? So this biases the transistor, no problem. We have done this till death, right? So yeah, source follower architecture or common gate or whatever you can think, you can name it. So this looks like if I do this, the transistor will be biased properly and looks like this node is available now. It's not ground. So if I connect, if I'm able to connect these two, and assuming that no loading happens, right? Then looks like I'll be able to get approximately V2, right? Yeah, in the negative feedback loop, it should get connected to the gate. Yeah. So that's what. So correct. So that point I agree. So you have to, but let's assume the problem is problem of sign, right? So we'll fix the sign later. Okay. So this is what we want to do. But if we directly connect V2 to if we directly connect through this green line, there is a problem, and the problem is the following. Can you comment on the relative strengths of these resistors with respect to the GM of the transistor? Like GM times R is more than 1 or less than 1? In order to, we wanted high loop gain, right? So GM times KR had to be much more than 1, which means these resistors are pretty large with respect to 1 over GM. Okay. Now, what is the input impedance looking here? Looking into the source, 1 over GM. Okay. So which means that this stuff on the right will get loaded over 1 over GM. Correct? So this is equivalent to saying I have a resistor here and I have V2 here. And this resistor is what, parallel combination of R and K minus 1R. And obviously since this R is much larger than GM, so this will load this will load V2. Okay. So that's a problem. We don't want that to happen. If we don't want that to happen, what can we do? Which means I have to put some block here. Which means I have to put some block here so that some fraction of V2 or V2 itself, or maybe some significant fraction of V2 appears at the source. Correct? So what should be the property of the block in terms of impedances? What should be the input impedance of this block? This is input, this is output. We want this V2 to be reliably transferred to the other side, or some fraction of V2 to be reliably transferred to the other side. In incremental sense, correct. Yeah, so input impedance should be high, right? We should no loading expected, so Rin should tend to infinity. And the output impedance should be, we want ultimately what? We ultimately want a voltage controlled voltage source in this case, right? We want V2 to be transferred to the other side, right? So this output impedance should be tending to 0. Yeah, why the output impedance should be 0? Is because you need to drive a low impedance load, right? 1 over GM is a low impedance load. So you are trying to drive that low impedance load without causing voltage fluctuations. So how do you do that? So if you have a network, this is RL, this is VI, and you assume that this is a voltage control voltage source, right? which has a resistance R out. This is VI. This is A times VI. And this is R out. And you want this output voltage to be also equal to A times VI. Then you want R out to be 0. Right? So this is the stuff inside the box, right? Okay. So it's basically, again, goes back to what type of control sources, when do you use one? Okay. So now, do you know of any control source which does this? It will not be infinity or 0, but reliably enough. I know, forget about gain of A. You can have gain of 1 also, or slightly less than 1 also, but it should be reliable. So input is infinite impedance, output is very low impedance for driving a very low load. We have only done finite number of types of topologies, right? It's one of them. Voltage buffer. Yeah. So what is a, I mean, what, do you recall a voltage buffer, or can you see a voltage buffer here? The same circuit, right? So all we need to do is this. So this is V1, RL, RD. We had this to be RD. And you had V2 here, which had a resistance. We wanted V2 to appear at this node. So all we need to do is pass it through a voltage buffer. And this will be approximately V2. Right? In the apps, if you assume GM to be very high and all those things, right? So we have done this. So this will be a source follower or voltage buffer or a voltage control voltage source, you name it. So now, can you comment on, let's assume these two voltages are quiescent wise, they are identical, right? So let's assume this voltage, this is V1Q, and this is V2. Right? So, okay, so I don't even have to assume this. If the loop works properly, right? If the loop works properly, then these two voltages will be identical. Correct? Which means whatever error amplifier I'm building, the input of those two error amplifiers will be identical. Right? So you can assume that these two voltages will be similar in terms of DC, which means if this is GM1, this is GM2, right? Okay, let's do the easy one first. So let's say we bias it in such a way that both are GMs. Same W by L. Same I0. Okay, so the quiescent wise, can you comment on these two nodes? Source of M1, M2. Will the source quiescent source voltage of M1, M2 be same or different? You seem confused. V1Q and V2Q are same. Yeah, because negative feedback loop will ensure they are same. So yeah, so value will be that, but the comment on the source voltages of M1 and M2, they will be same, right? VG is same, current is same, yeah, same, everything same, they will be same. So if I connect these two, there won't be any loading. There won't be any DC current flowing through that short. Okay. Otherwise, I mean, we can as well connect a very large capacitor if you're not sure whether they are planning to load. But in this case, it's not loading, so we can as well connect it. Okay. So if that happens, what will be the incrementally, what will be the voltage at this point? You can do this using superposition. right? So you assume this, there are two inputs, V1 and V2. Okay. You assume two inputs, V1 and V2, and use superposition. So first thing I will do is let's say I say that V1 doesn't exist. Superposition, I can short one or desensitize one input and take the other input and do the vice versa. Right. So let's assume V1 is not there. Right. If V1 is shorted, what will be this current? What will be the incremental current? So this impedance looking up is 1 over GM. So this is equivalent to, if I break the circuit down, this is equivalent to incrementally correct. So this voltage will be what? This will be GM V2. So if this is R, for example, so this voltage is GMR by 1 plus GMR times V2. Right? Standard circuit, we have done it multiple times. In this case, R is equal to 1 over GM. So this will be V2 by 2. Right? So you see that full V2 is not getting translated, a fraction of that is getting translated because it is still loading. Okay. So this becomes V2 by 2. If this is V2 by 2, what is the incremental current? This is V2 by 2. Incremental current is GM V2 by 2. Correct? So the current that is flowing, incremental current that will flow in this direction, and the value will be GM times V2 by 2. Now you do the same thing with the input at V1 and shorting V2. So I short V2 and apply V1. What will be the incremental current? Same thing, same expression, but in opposite direction. It will be GM times V1 by 2, right? It will be GM times V1 by 2 in the opposite direction. So what will be the net current that is flowing? No, if V1 and V2 are, you don't assume V1 V2 to be 0 to start off. Let's say that they are something different. If they are identical, it will be 0. But if they are not, then the current will be GM times V1 minus V2 by 2. Correct? And question voltage is okay. So everything will not be, if the gains are not infinite, there will be some error. The question voltages will not be exactly same. It will be slightly different, but we are neglecting that slight difference in terms of figuring out the question. Okay. So this seems like, I mean, this, okay. So this is the incremental current. This incremental current is flowing into RD. Right? So this incremental current is flowing into RT. The voltage that will accrue here will be what? No, it's this current times RD, right? This current times RD in a negative direction, because the net current direction is coming out of RD. So this will be your, if this I call it to be V0, your V0 will be this. So this seems like minus GM by 2 RD times V1 minus V2. Okay, so this behaves like, this almost behaves like a common source amplifier having a gain of minus GM times RD by 2. And this should not be surprising, because ultimately we wanted an output to be equal to some common source amplifier, right? We wanted to feed the input. We cannot directly feed because it's loading. We are using another transistor, another buffer to feed. And naturally, the expression should be similar to that of a common source amplifier, but it's not identical, because still we have some loading effect. And because of that, we are losing a gain of 2. But we still, I mean, we would be able to figure out I mean, if GMRT is much greater than 1, GMRT by 2 is probably also much greater than 1. So with an error of half, we can still design something, right? So let me take one more minute to make that point that came out, that it seems like there is a flipping of sign that has happened, right? We wanted VF to be here, right? Where was it? We wanted this, right? We wanted VF minus V1, but we ended up with V1 minus VF, correct? So if I sketch this circuit again, this was supposed to be VF. This became minus GM by 2 RD V1 minus VF. Correct? So if we want a flipping of sign, what should I have done? I should have had to apply, I ideally should have had applied VF here and V1 here. Right? So just I have to take the same circuit, flip and don't connect in the way we started the common source amplifier. You'll have to, now you have two independent inputs. You can connect either input to any of the input ports without being concerned about loading, because now you have two transistors, you are looking into the gate, right? And none of the transistors will be loading the previous case because the input impedance is effectively infinite. Okay. Okay, fine. So this is something that we call a differential amplifier. We will spend next couple of classes on this. Extremely important circuit. So many variations available. So we'll spend some time on this. Okay, thank you.